But as you can see, the focus is on horticultural cropping systems, so relevant to a number of SDGs, certainly number 2 for food security, certainly 3 for human health. We're all supposed to eat more fruit and veg, and perhaps we should be producing more of our own fruit and veg as a nation. And in terms of the SDGs, it's certainly relevant for number 15 on land degradation. We want to grow more fruit and veg, but can we grow it in a more sustainable way? And what sort of condition is the land in on which we're growing our fruit and veg? So before I move on, I need to acknowledge the funding from the Agriculture and Horticulture Development Board. The project was very much to do with soil health, but also precision farming. So it was looking at a soil survey of land under horticultural cropping systems, and then 6 demonstrations to do with precision farming and horticulture, which was sort of steered and led by a grower and advisor group. I acknowledge my co-authors, Dan Munro, who did much of the work on the ground, Lizzie Sagu, who led on the soil mapping work I'll talk about in a minute, and Joanna Cloyd from SRUC, who led on the work in Scotland. So what I want to cover is, first of all, the challenges of horticultural cropping systems from a soil management perspective and from a land degradation perspective. Secondly, a report on a soil survey which focused on soil physical quality, so what sort of state are our soils in under horticultural production. And then focus on one of these 6 demonstrations which looked at soil mapping for horticultural growers. What are the options in terms of soil mapping and using soil nutrients more effectively and more precisely? And then finally, look at some of the soil management guidelines we've produced with AHDB, which wrap up some of the findings of these different demonstrations. So moving straight into horticulture and the challenges of horticultural cropping systems. A lot of the crops are grown in double cropping systems. A lot of cultivation involved. There's challenges in terms of reduced cultivation within horticultural cropping systems. They're often grown within rotations where there's a number of different crops, a number of different machinery types, and so the footprint of production is quite high in terms of the amount of land that is compacted. The other challenge is that they're grown under contract, so there are precise dates for drilling and for harvesting, and a lot of the crops are late harvested, so can be harvested in sort of less than ideal conditions. So you can result in situations like this. It doesn't have to be like that. We can do better than that with more planning, even just simple, more organisation in terms of routing and even controlled traffic farming systems. But these are the challenges that growers are presented with within their systems. So what sort of state are our soils in? Well, we did a survey across England and Scotland, so all the way from almost the tip of Cornwall up to Angus in the northeast of Scotland, across 75 fields on 49 holdings, and that included annual crops and perennial crops. Today I'll focus on annual crops, so the alliums, brassicas, roots, salads and vining peas. And on those fields, on those annual cropping fields, we looked at the soils pre-planting and post-planting. So we could look at the state of the soil post-harvest, if you like, before any preparatory cultivations, and then we could look at the soils again post-cultivation to see how effective those cultivations have been in producing a good plant growth medium. So what did we do? On each of the fields that we went to, first of all, we went across the field 20 times with the cone penetrometer, just to look at the level of resistance in the topsoil into the subsoil. And then we used those measurements and picked out those spots we had the minimum, the medium, and the maximum penetrometer reading. And at those 3 points, then we then did some more detailed investigations. So we looked at a bulk density profile, which I won't focus on so much today. So we looked at bulk density at 3 different depths down through the soil profile. And we also did 2 different types of visual soil assessment, which I'll show you a little bit about. So 2 different methods, visual soil assessment method from New Zealand and visual evaluation of soil structure method which was developed by SRUC, Aarhus University, and Tom Beatty. So I say this was done in 3 locations in each field, both before and after cultivation. So I just want to focus on the VSA, the Visual Soil Assessment, and what we found there. And what we found was that before planting, before any cultivations, this was the sort of typical condition of the soil. This is just illustrating one of 6 visual indicators which form part of the Visual Soil Assessment method. So this is the structure and consistent score. So that involves taking a block of soil, spade width, spade depth, and dropping it from about a waist height. It's called the drop shatter test, and then organising the aggregates largest to the top and the smallest to the bottom. And what you end up with is really the largest aggregates to the top indicate the degree of a tillage pan being developed, and the small if you've got more small aggregates, you've got soil in generally better condition. But we found that most of the soils pre-planting were coming out as moderate status, so in this sort of condition. And it was across peaty soils and medium soils. This is just an example for soils before lettuce at 3 of the sites. So 55% of the soils were in that sort of condition before cultivation. Post-cultivation, we ended up with 42%. So we've gone from 55 to 42% of the soils being in moderate condition based on the VSA score. So some progress. If your glass is half empty, you're thinking there's 42% moderate condition and there's none poor, which is good news. If you're more an optimist, you're thinking, well, we've increased the number in good condition from 40% to 58%. But the poor really does need to be in very poor condition. All the aggregates need to be virtually all are in this sort of size to qualify as poor condition. So that's the results in the VSA score. One element of the VSA score is the presence of a tillage pan. So at each of these sites we could see again pre and post planting how many sites had a well-developed tillage pan or a moderately developed tillage pan. And again, this is the post-planting score. We found that around 60% of sites had a tillage pan, 42% post-planting had a well-developed tillage pan. That means that layer is severely consolidated, there's no macropores, and very few cracks in it, and very little, if any, structure at all. So it implies that, indicates that there are some sort of structural challenges, structural limitations in the profile. So in terms of the overall summary of the survey we did as a whole, just to summarise quickly, we found a well-developed tillage pan in 60% of the soils pre-planting, but even post-planting, post-cultivation, we've still got 40% of those soils with a well-developed tillage pan. From the bulk density point of view, we compared the bulk density levels we saw with the UK Soil Quality Indicator Consortium levels, which relate to the organic matter content of the soil. We found that half of the top soils were above those bulk density concern levels, and 70% of subsoil. So there seems to be an issue with our subsoils in terms of bulk density. Alongside this survey, we also did a survey of soil management, so we could link the soil management to a degree to the soil condition. And we found, based on the soil survey and questionnaire and interview, that many cultivations are carried out routinely, such as subsoiling. So people are subsoiling whether they've got a soil issue or not. And all of this has implications for crop net margins and business profitability. We found in some cases where the grower was forced to go in and cultivate in suboptimal conditions, resulted in moderate or poor soil structural condition, and actually resulted in crop disease that meant that the whole crop had to be discarded. So there are implications. So that's the soil structure side of things. I just want to now focus on one of the 6 demonstrations that we did as part of this project for AHDB. So this is looking at soil mapping and how growers can use different methods to map soil variability and then manage it. Now, not all our landscapes, not all our fields are very variable. The soils aren't very, very variable in all landscapes, but certainly in those areas where we have glacial fluvial outwash deposits, such as in parts of Bedfordshire, the fields can be very variable. So what we did is we looked at a particular field where there were 4 or 5 different soil series, and we sampled it to death basically, and looked at different methods of sampling it to capture that variability and think about how to manage it. So this is a field called Avenue Field in Bedfordshire, a 10-hectare field. The topsoil texture varied from a loamy sand down in the sort of southern part to a heavy clay loam in the top half. As I say, we grid sampled it, area sampled it, zone sampled it, and used different mathematical interpolation methods to come up with maps of that soil variability in terms of nutrient reserves and pH. So we first of all did the classical method of doing a W, so 25 cores across the whole of the 10 hectares to give us an average soil pH, pK, and magnesium value for the whole field. And then we did what some of the commercial companies do. One of the services that is offered is to split the field up into polygons. So we also did that. And then we did a W in each of the polygons to see how the soil pH and nutrient levels varied in the different polygons compared with the whole field. And then we also did the grid approach. So this is where you actually go to each point within a grid and take 16 samples in the spiral around that point, and then use mathematical interpolation methods to determine what the nutrient levels or the pH is between those points. And then we really went to town and sampled the whole lot on a 25-metre grid so that you could see how the map changes as your resolution increases. So that's the area or grid-based approach. We also looked at a zone-based approach, which might appeal more to the pedologists amongst us. So here we could be using soil brightness or electromagnetic induction to determine where the soil boundaries are, and then we go in with a soil auger to determine what those different soil units represent. And we come up with a map like this, which shows us different parts of the field with different soil series, heavy clay loam over clay here compared to sort of loamy sand over sandy loam down at the bottom. So splitting our field up into different soil units based on scanning technology and soil survey, traditional soil survey methods, and then actually sampling within those different zones and managing it accordingly. So those are the different methods we looked at. And first of all, just to tabulate the lot, if we look back at the 25-metre grid which we sampled, we can compare the results from that grid with the whole field method, and we can see that the whole field results are concealing a fair bit of variation. So we just look at the pH to start off with. At the whole field level, it's suggesting we might need a little bit of lime, but whereas if we look at the 25-metre grid across the whole field, we've got some parts which are in desperate need of lime and others that don't need it at all. Quickly look at the phosphorus. It's similar in that there are parts of the field which need just a sort of a top-up or a maintenance of phosphorus, phosphate fertilizers. Others need it a bit more, and others don't need it at all. So there's a fair bit of variability across the nutrients, and there's variability in clay content here, as we see. So we looked at the different methods. So to look at the grid, let's look at the grid method first. It's useful in some ways just to look at the values. This is focusing on soil phosphorus, or soil extractable P. Just looking at the values at each grid point gives us an indication of the variability across the field. This would be very expensive and far too expensive for a commercial operation, but this is one way of looking at it. If we plot that up using an inverse distance weighting interpolation approach, we get this map, which shows us this degradation from sort of low P down to sort of higher P at the bottom. So variability in terms of how much P is needed. If I flick through, we go from a 25-metre grid, 16 samples per hectare, to a 50-metre grid, slightly less resolution there, slightly less detail, to a 2 samples per hectare, which brings out these sort of curious islands of low P for some reason. And then what would normally be done on a commercial basis is sampling on one sample per hectare, which gives us a bit of a gradient from sort of northeastern part of the field across to the western part of the field. So that's what we get if we use an interpolation method. If we split it up into polygons, we get a similar sort of pattern to what we had here, but just using polygons, and this is quite easy to manage from a fertilizer application point of view. At that sort of resolution, we can variably apply a phosphorus from a twin disc spreader, for example. So that's the polygon approach. Using the soil survey or podology approach, we get that. Again, we can manage that quite easily using a twin disc spreader and GPS. And then finally, just to show you the level of confidence you can have in the interpolation methods. It didn't matter which method we used at this resolution, you get a similar pattern, whether you're using IDW, Cryogene, spline or natural neighbour, you get a similar map at the 25-metre grid resolution. If you bring the resolution down, it actually changes quite a bit depending on which interpolation method you're using. So it's a question of choice and different options for the growers. So just a summary, that the key messages really are whole field soil sampling. Certainly in this sort of landscape, this glacial outwash material landscape, which is very variable, the whole field soil sampling can seal significant variability within the field. But the benefit and opportunities from soil mapping and variable rate fertilizer, they'll depend on the level of the soil variability. In this sort of situation, we've got high P and low P areas within the field. There could be benefit from evening that up by sort of varying your application rate of phosphorus, varying application of lime. Wouldn't necessarily be the case in all cases. So our advice to growers that are new to precision farming techniques is that the tools out there, they can help you to understand your soil variability and then how to manage that soil and crop variability. And the first phase is really sort of data gathering exercise, so using multiple data layers. So they can use yield mapping data from cereal combine harvesters. And they also use soil mapping information to sort of build up a layers of information in terms of how their crops and their soils vary over time. And then understand it first and then decide how to manage that variability. Just very quickly then, just to show you what all this work's been put together into. The output, to one of the major outputs of this project was the Soil Management for Horticulture booklet, which HDB had produced, which gives guidelines to farmers about how to manage compaction, issues of compaction. We tried to get them in touch with their worms. There were certainly some indications from the survey that the fields that had cover crops or that were in orchards had higher earthworm numbers than fields that hadn't had cover crops, for example. So get in touch with earthworm numbers and earthworm types. We did one demonstration on controlled traffic farming, so there's information there about what they've done at Barfoot's farms down in Hampshire, where they've gone from a purely sort of plough-based system, lots of different types of machinery and a very heavy footprint on the soil, to a strategy based on reduced tillage, controlled traffic farming and cover cropping. So there's some information there. And then some more information about the impacts of wheel load and tyre type and size on soils, and how we can avoid some of the worst compaction issues. So that's it. That's what's in the guide, focusing on the importance of good soil structure, how important it is for production, and how important it is in determining the environmental footprint and impact of production. There's information on there on how to assess soil structural conditions, different options of doing that, but getting a spade out and having a look. Strategies to improve and maintain soil structure, so everything from avoiding compaction in the first place to how to alleviate it if you've got it, change your cultivation system, and then information on the precision farming techniques, measuring and managing soil and crop variability. So that's available now on the HDB website, and if you want to follow everything that HDB are doing on soil management, hashtag Great Soils on Twitter is the place to go. Thank you.
Any quick questions for Paul?
Can I just ask one question? You said that 70% of subsoils had fault densities that were too great for crop growth. Was that taken into account natural compaction in subsoils as well?
It was using the UK Soil Quality Indicator Consortium guideline values, which are soil type related. Yeah. So they're different for clay soils, lighter soils, and peaty soils. Yeah. So it's just using those trigger values and seeing how many were well above that level, that concern level. So it's more of a statistical guide than related to soil function, really.